We will now move on to learning from the experts on plastic pollution. We have assembled an extremely talented group of researchers and practitioners from all over the world who will share their expertise on microplastics. We welcome you to use the question and answer function to pose questions to us during the panel discussion, as the speakers provide their remarks, or during the speed round of questions that we'll have after some remarks from each of the panelists. We will try to answer as many questions as we can live during the panel, or we will follow up with you afterwards to answer any other questions you may have. It is now my pleasure to welcome the moderator of the panel, Professor Shooka Karimpour. Professor Karimpour is an assistant professor of environmental hydrodynamics and civil engineering department at York University. Her research team investigates the physical processes shaping the distribution of sediment, air, and contaminants in water. Thank you, Shooka, for taking the time to be our moderator today. Over to you.
Thank you very much, Professor Sharma, for that wonderful introduction. Hi, everyone, and welcome to today's panel. I'm very pleased to be sitting amongst you, our guests, our host, and our esteemed panelists. And today we'll be discussing about one of the most important and critical environmental crises of our time, plastic pollution. As Professor Sharma wonderfully explained, my background is in hydrodynamics, specifically related to the environment. And one area of my work is to look to see how the movement of water in lakes and rivers affects the mobility of different matters, from air to sediments to contaminants, including plastics and microplastics. So when it comes to plastic pollution and their mobility, we really, in the aquatic system, in our ocean, we really see plastics reported widespread from their resources across the ocean. And in fact, one of the earliest reports, scientific reports of plastic debris, floating plastic debris in ocean gyres, converging ocean currents in the middle of the ocean, dates back as early as 1972. So plastic pollution is technically in water. It's a problem we know of for more than 50 years. But over the last couple of decades, the excessive use of plastics and really with it exponential growth of plastic production has really intensified the situation. And when we talk about aquatic plastic pollution, there are numerous sources to plastics. And however, majority of it is unfortunately land-based. We have plastics that are emitted from wastewater outlets to stormwater runoffs and from processes such as windage. And we also have plastic emitted to the ocean, to the water through sudden event, flash flood, tsunami, which can be actually intensified by processes such as climate change. And for example, one example of it that is eye-opening is that Tohoku's tsunami in 2011 emitted so much plastic that exceeded that year's emission for any single country. So what we really see as a plastic pollution, what is observable to our eyes, is, I would say, is really the tip of the plastic iceberg. And when it comes to microplastics and nanoplastics, plastics that are smaller than 5 millimeter and those are smaller than 1 micrometer, we really have a big problem. Because these small particulates, they're going to remain suspended in water for a very long time, and they can get transported to very, very remote distances from the source. And really, there is alarming number of reports really showing the presence of microplastics across every corner of our water bodies. Besides, to make situation worse, when what we really call plastics and microplastics I would say it's a very loose definition of these matters, because what happens is that plastics have a lot of different physical and chemical properties. And because of that, the solution to tackle plastic pollution is not a one-size-fits-all. And there is also an alarming rate evidence that is emerging in scientific community showing the adverse impact of plastics and microplastics, not only on human health, but also on ecosystem health as well. And unfortunately, plastics and microplastics do not affect health in one single pathway. They actually impact health in multiple pathways, as you can see in this image presented in front of you. So with that, I have to say I've painted a gray image of plastic pollution. But I have to say, I also see a light at the end of the tunnel. There is a lot of awareness around plastic pollution. There's a lot of meaningful and promising research activities.
Il y a des recherches qui sont très prometteuses à l'échelle mondiale sur la pollution plastique.
Of solution that being worked on, and I think there is on the way on plastics as well to tackle plastic pollution as well. And today, we are in it for a treat. We have gathered a wonderful set of panelists that are activists, scientists, and researchers from across the globe who have expertise on these topics from transport all the way to source. And we have them over here for you. So our panelists are we're going to first hear from Professor Denise Mitrano from ETH Zurich, followed by Madame Jacqueline Mbocksi, who's the president of GWP Cameroon. After that, we're going to hear from Dr. Zhijie Li, who is joining us from UNiTAR. And finally, we have Professor Satinder Brar, my colleague and my friend, who is also joining us from York University. So without further ado, I'm going to introduce our first panelist who is joining us from ETH Zurich. And we have Professor Denise Mitrano with us. Professor Mitrano's work focuses on distribution and impact of anthropogenic material in environmental systems. She is particularly interested in developing analytical tools to systematically understand the mechanism and processes that drive the fate, transport, and biological interactions of particles, including particles of concern that are nano and microplastics. She has been recognized really through numerous awards, including just one single one that I'm going to point out, and that is Swiss National Science Foundation Award, Mary Heim, for Outstanding Young Woman Researcher of the Year 2021. And with that introduction, Professor Mitrano, the floor is yours.
Great. Thank you so much for the introduction. As was mentioned, my name is Denise Mitrano, and I'm Professor of Environmental Chemistry of Anthropogenic Materials at ETH Zurich. So in our team, we're looking at the movement and transport of particles in different environmental systems, mostly water and soil. And in the last several years, our team has been specifically focused on the aspects of plastics pollution, including microplastics and nanoplastics. So for today's seminar, I was asked to talk a little bit more about these mechanisms which control fate in water and how this impacts different natural systems. So we've already been introduced to the topic of microplastics from the previous speaker, but I just wanted to delve in a little bit more detail about where these microplastics and nanoplastics come from. Now, some of these materials are already produced and used directly in different types of consumer products. These are called primary microplastics, which are used in body scrubs or in agricultural fields for agricapsules and for seed coatings. However, the vast majority of microplastics and nanoplastics come from the fragmentation of mismanaged plastics waste. So this can be when soda bottles or plastic bags are littered, or also from just using the types of materials that we have every day that are made of plastic, which break down during their use, such as textiles and tires. So together, these different pieces of the puzzle come together of how many different types of microplastics pollution there are, which include a lot of different types of polymers and plastic added chemicals. Now, we had also heard that plastics pollution is a big problem overall, but that there are specific impacts which are associated specifically with these smaller sized particles. And so if we look across the size continuum of plastics pollution, we'll also see different impacts on fate and hazards. So if we start with this macroplastic pollution, the soda bottles, plastic bags, things like this, larger organisms can directly get entangled in these items or consume them. However, as plastics fragment through UV and mechanical stresses, they can form microplastics, those particles which are 5 millimeters and smaller. Because of their smaller size, they can be directly taken up into organisms or also aggregate with other natural particles which are in the environment, which might ultimately change their fate and transport. Now, the fragmentation doesn't stop there at microplastics. We can also get particles of smaller size, nanoplastics, which are formed, which are those particles that are 1 micron and below. At this smaller size, we can have increased transport, either through water, soil, or air. And we can also have different types of biological interactions, including crossing biological membranes or potentially being taken up into cells. As with all particles, the smaller the size is, the larger impact the surface area has. And with an increased surface area, we might have an additional leaching of additives as well from these different smaller sized particles, which might have their own negative environmental and health effects. So now, with this information in mind, looking at this size continuum of plastics pollution, you might be thinking to yourself, okay, we have smaller plastics, so do we actually have bigger problems? And I'm sure you've all seen headlines such as these in the local media, that there is some beautiful place, but it's poisoned by microplastics. There's microplastics found in the snow from the Alps to the Arctic, so it's everywhere that we're looking. There's microplastics in our drinking water, and are we even eating our fleece jackets because there's microplastics in our food? So now this is a little bit of hyperbole and a bit of clickbait about what sometimes the public media presents as an issue with microplastics. But what do we as scientists think about this aspect? So what is really known and what is unknown in this area? So we know that even though there's a lot of studies being done, the eco and human toxicological effects remain really uncertain. And it's not clear if this is from the plastics and polymers themselves or from the plastic added chemicals. Well, we know that there's plastics everywhere that we look. There's really little information on the dominant fate and transport processes, how they're actually getting from point A to point B. And that makes the risk assessment in terms of both hazard and exposure subject to large uncertainties. But what we do know is that microplastics and overall plastics are a very persistent material, which are widely dispersed among many ecosystems, and there's unknown ecological consequences. And so that's exactly what we're trying to study now. So why is it so challenging to be able to understand where these plastics are and how many there are? This is a little bit about challenges of detecting particles overall. When we think about microplastics or nanoplastics in an environmental water system, we have to change our mindset to how we normally think about pollutants in an environmental system in terms of their fate and transport, the different risk variables that are associated with it, and developing new methods. This is because there's a lot of challenges specifically with particles analysis in comparison with dissolved chemicals, because we need to be able to differentiate particle types, oftentimes having very low concentrations and small particle sizes, and these particles may transform over time. Now, when we think specifically about the challenges of detecting and characterizing nano and microplastics, this is a very heterogeneous group of materials made up a lot of different types of polymers and plastic added chemicals. And currently the bottleneck is at the analytical methods. It's very time consuming to be able to measure these different environmental samples, and there's no standardization in the field yet today. So it's a little bit challenging to compare different studies. Furthermore, we may have very high detection limits, both in terms of the particle size and the concentration which we can measure. Now, this gives several different implications about what we can actually say about the particles that are there, because we can only have a limited number of samples that are taken because it's so long to eventually analyze them. And this makes mechanistic studies very time-consuming, often in the laboratory as well. So this gives us a really reduced understanding of basic processes of how particles behave in the environment. And so in that context, it makes it difficult to have a risk assessment of plastics in the environment now because of these analytical bottlenecks. But before we dig so much into this aspect of what we're measuring and how we're measuring it, I think it's nice to take a step back to more frame this issue of microplastic pollution in the environment. What does it really mean that plastics are there? Now, a lot of researchers, ourselves included in our lab, take a microplastic-centric view of the research. So the questions can be, what are the microplastics that are there and how many? What are the different properties and what are the chemical transformations that might happen? How are they transported or how are they ingested by organisms? And so this type of research is always following what is happening with the microplastic. But I'd like to invite you to think about it in a different way as well, which is in an environmental systems view. So how are these microplastics actually interacting with natural systems? And are there also impacts on biogeochemical cycles or different aspects of ecosystem surfaces? In this way, are there indirect effects on ecosystems and health? And if we take this One Health perspective, we may be able to understand a little bit more about the myriad of impacts that microplastics may have. So now if we think specifically about the transport dynamics of microplastics in freshwater, microplastics aren't there alone. There's a lot of other particles there as well, natural particles. These can be organic materials, mineral particles, or small biological organisms like algae. Now, when all of these particles get into a certain system, they can have different fate and transport processes. Sometimes this is dependent on the material itself. So if you have a plastic which is more light, it might just float. And if you have a more dense plastic, then it may settle. But we can also have interaction with these different natural particles by forming different types of heteroaggregates or having a biofilm that is formed on the plastic, which will change their transport behavior overall. Now, this is a lot of different variables that we need to cover. So the microplastics' fate and transport is still now quite ill-defined by unknown settling rates and dynamics, especially how it's interacting with natural particles. So even though there are a few studies that are looking at microplastic settling dynamics, this is normally on a relatively limited number of particles in a laboratory, even in a laboratory setting, and doesn't include this interaction with other natural particles. So one study that I'd like to present you today is how microplastics influence their settling dynamics with freshwater snow. So what is freshwater snow? It's a natural heteroaggregate of algae, particulate organic matter, and trace inorganic materials. So when you go swimming, you might see this kind of fuzzy stuff in the water. This is what is the freshwater snow. And this material is really key in biogeochemical cycling of nutrients from the water surface to the sediments. And so we want to see how microplastics impact this natural cycling of materials. So when we come back to all the different ways that microplastics can be transported in fresh water, we're specifically looking at this section circled in red now, the heteroaggregation of microplastics and these natural particles, and how it can impact the settling dynamics. So here we wanted to make an experimental design to measure the large number of settling particles in our experimental system and be able to quantify the settling rates of microplastics that are different sizes and different polymers, either alone or when they're aggregated with the freshwater snow. And furthermore, we wanted to see if these microplastics change the settling rate of the freshwater snow, since this may have impact on natural nutrient cycling. So to do this, we needed to track microplastics and aggregate settling dynamics. So we can make a laboratory column in the lab and put microplastics or freshwater snow alone in this column, and then measure through a series of cameras how fast they're settling. We can then also make heteroaggregation between these microplastics and algae, and then put these heteroaggregates into the column as well. With this type of experimental design, we can track thousands of particles settling simultaneously with our laser tracking system. So here we have a 1.5 meter column, which is illuminated by laser lights, and put in our microplastics at the top of the column, or our freshwater snow or heteroaggregates, mix them at the top of the column with a stir bar, and watch them settle over time. Now, to dissipate some of the turbulence which is caused by mixing them in the column, we have a filter to dissipate the turbulence, and then have a series of cameras with optical filters to be able to see where the microplastics are settling and how fast they are settling. So when we start to look at the influence of microplastics and freshwater snow on settling, we can first look at these high density microplastic fibers and fragments, where all of these plastics are more dense than water, and the larger the particle size, the faster the settling rate. Now, this makes sense because if you have a higher mass, this is settling faster through water. But what's interesting to note is that the shape is also quite important. The first 6 bars on the graph on the left are all fragments, so irregular spheres. But we can see that fibers, which have the same mass as the large size fragments, are settling significantly slower. This is because of the way that they orient in the water column, and therefore it changes their settling rates. So now what happens when we add freshwater snow to the mix? Here, if we look in just the brown box, we can see the settling rate of just the freshwater snow. And then in the purple and blue shades, we can see their aggregates with different types of microplastics. So we can see that we can increase the settling rate of the freshwater snow when we have microplastics that are aggregated inside, because this is a heavier ballast, which helps bring these freshwater snow flocks faster towards the sediment, which can ultimately change the cycling of nutrients of this freshwater snow in these natural cycles. Now, if we compare now the measured velocity that we have measured from our previous experiments to Stokes velocity, which is the estimated or calculated settling rate of a spherical particle of a given size and density, we see that the different
de particules sphériques. Nous pouvons voir que différents plastiques sont beaucoup plus lents à se stabiliser. C'est en raison de leur forme atypique. Il y a des calculs qui sont utilisés pour modéliser ce calcul et nous devons l'adapter aux microplastiques tout en prenant en compte ces caractéristiques. En résumé, lorsque vous vous penchez sur l'interaction entre les microplastiques et la FWS, il y a une influence. Donc, la morphologie des microplastiques doit être considérée lorsque vous évaluez le taux de stabilisation et l'agrégation va augmenter les dépôts de FWS dans la colonne d'eau. Nous avons collecté un grand nombre de données qui peut être utilisées à l'avenir pour mieux comprendre la façon dont les microplastiques traversent les différents plans d'eau. Donc, sur ce, je remercie mon équipe ici à ETH. Merci de m'avoir permis de conduire cette recherche sur ce sujet et d'autres, et j'ai hâte de discuter avec vous plus tard dans le panel. Merci. Merci beaucoup, Denise, pour cette excellente présentation et vos recherches sur le transport. Je suis d'accord avec vous, la détection peut être difficile et une tâche onéreuse.
Understand the risks of microplastics. So thanks again, Denise, for that wonderful presentation. Our next presenter is going to be Madame Jacqueline Elizabeth Mbocksi, and her presentation is going to be in French, so please do not hesitate to use the interpretation button at the bottom of the Zoom panel to switch languages. So Madame Jacqueline Mbocksi is a socio-environmentalist and expert in social environmental management of projects. She's had a brilliant career at the Douala urban community, where she has led the Department of environment and living systems. She participated in the development and implementation of many major projects in the city of Douala, including C2D project and Douala's stormwater system projects. She is currently associate professor with the University of Douala, and the president of GWP Cameroon. So with that, Madame Mbocksi, s'il vous plaît, allez-y.
Bonsoir à tous. Merci pour cette présentation et je vous remercie de nous avoir invités.
Introduction, and thank you to have invited me so I can invite you to speak. Thank you to have invited me to speak on pollution in the city of Douala. Plastic pollution is something that has as well. So thank you to have given us this opportunity. First of all, I need to introduce you my city so that you can understand
pour que vous puissiez mieux comprendre l'impact que la pollution plastique cause dans cette ville. Alors, vous pouvez avancer, s'il vous plaît. Vous pouvez avancer. Voilà. Notre ville est située, c'est une ville côtière. Douala, c'est une ville qui est dans l'eau. Nous l'appelons toujours la ville de l'eau. C'est une ville qui est côtière, elle est située à 30 km de l'océan Atlantique, au fond du golfe de Guinée, dans l'embouchure d'un fleuve appelé Vouri. C'est une ville qui a...
of the Wouri River. Douala has 6 arrondissements.
Elle est peuplée d'environ 5 millions d'habitants. C'est une ville qui a un climat de type équatorial humide. C'est composé de 2 saisons de pluie qui durent environ 8 mois et elle s'étend, et une saison sèche qui dure environ 4 mois. Son réseau hydrographique, dont le principal fleuve qui compose ce réseau, c'est le Vouri. Mais le Vouri est constitué aussi, son réseau hydrographique aussi constitué de 9 versants hydrauliques que nous appelons généralement les drains qui se jettent dans le Vouri. Je crois que la figure en dessous va vous montrer vraiment comment est-ce que toute cette ville est une ville immergée d'eau. Bon, nous, à côté de son réseau hydrographique, il y a le climat. Le climat de Douala, c'est un climat qui est du type équatorial humide.
Is equatorial. It is humid, like I mentioned, with a very long rainy season and a very short dry season. We have
bas et cisaillé des vallées encaissées
cut by deep valleys of the Wouri tributaries. In terms of its geology, Douala lies on the coastal sedimentary series of the basin, which extends over an area around 7,000 square kilometers. The soils are ferrolitic on the emerged parts and hydromorphic on the coastal edge. So here you have a short overview of the city of Douala. This is what I had just presented. Now, let's turn our attention to waste. We can move to the next slide. Next slide, please. Next slide, please. Thank you. So here's our city of Douala. You can see that the city is in the waters. Everything you see here shows you that the water is completely immersed in water. The city, rather, is completely immersed in water. In Douala, what are the sources of waste? We're going to give you an overview of where does the plastic waste comes from. Our city is first and foremost an economic capital. It is home to most of the country's plastic producing industries and companies, some 160 of them. These industries will produce plastics that are located in the city itself. They produce, market, or import plastic, especially non-biodegradable plastic packaging. However, if we could assess the plastic, we would be able to tell you that in 2019, we have produced 2,000 tons of plastic. And of this 2,000 tons, 5% was collected and 1% of that waste was recycled. 14% of the remaining, well, 14%, you're wondering plastic was not collected nor recycled. So what happened to this plastic? And that is our challenge and the big issue that our city faces. What happens to non-collected, non-recycled plastic? This is the big question that we are trying to solve. So let's continue. Let's look at the types and proportions of plastic waste. Next slide, please. We have, for example, PETs. This is 31% of the production. There's also 35% of low-density polyethylene, 10% of high-density polyethylene, and 2% polypropylene. So how do we manage this waste? Well, in fact, there are laws that manage the disposal of waste. And in this law, all of the major players are identified. However, the law for the decentralized territories are different in terms of transportation, collection of waste, treatment, management of waste, and there's also governmental actors that are policymakers and that support the implementation of these laws. They also contribute to awareness raising. We also have international and national partners to that effect. Next slide, please. Next slide again. Next slide, please. We've already covered this. The impact of plastic in our city is multi-pronged. First of all, there is an environmental impact. When you walk in our city, you will see there's plastic everywhere on the streets. There are impromptu plastic deposits. Uncollected and unrecycled plastics will also go into our waterways. Our chairperson today spoke about the impact of microplastics and its impact on organisms such as fish. The environmental impact also includes mangroves that are under attack from plastic waste. Plastic also has an economic impact. In fact, it has a major impact. It will directly affect fishermen's jobs, and they are seeing a significant drop in their catch. Most of the population depends on fishing activities for survival. And these plastics are sometimes also found in agricultural soils, which has a negative impact on yields in these cultivated areas. Because most of the plastic that we have in the city are non-biodegradable plastic. There's also an impact on tourism. It's not pleasant to walk in a city littered with plastic. We will try to, after going over these impacts, we will show you the situation in the watersheds. Not everywhere in the city, but in key areas of the city. I forgot to mention, there's also a social impact. All of this non-collected, non-recycled plastic will be dumped in rivers or drains, and that will obstruct the passage of water, causing flooding, severe flooding. There are also other consequences because it will create the development of waterborne diseases such as typhoid fever, malaria, and the accumulation of plastic waste generally constitutes a favorable environment for the development of disease vectors in a country where our healthcare is already under pressure. Not every person in Cameroon lives in good conditions, and therefore there's an impact on health as well. So that you can measure the scope of the issue, let's look at the next slide to paint a picture of the situation in the city.
Next. Prochain slide, s'il vous plaît.
Next slide, please. Here we are. This is what the city of Douala looks like. The presence of plastic waste in nature can be observed throughout the city of Douala. You can see that in all of our watersheds, they are in this state. These are the main sites where plastic waste has been observed, and you can see it in the pictures below. Plastic is in the drains, in our watersheds. This is the result of human activity. We don't have a good triage system yet. And we don't have a good waste collecting system either, nor do we have a good transport system. At home, despite all of the awareness raising campaigns, despite all of the advice received, the population is not able to contain the amount of waste that is generated. All of the waste is mixed together and collected by the communities. And it goes towards the same place. The city doesn't collect all of the waste produced because of our financial limits. We're not even able to collect regular household garbage. All of this plastic, all of the kinds of waste is all mixed together.
The city doesn't have the capacity to collect all waste. Only 30 to 40% of the waste is collected, so there's 60% left there. All that goes to the ocean. All the drains go to that river and then to the ocean. You can move to the next slide. So I was told that I should share something with you. The concept of shore to sea, or source to sea, rather. We initiated certain actions. The goal is to be a city that will improve living conditions for the citizens. So we created documents, a strategy, Agenda 2021, or Agenda 21, rather. We gathered share stakeholders, people involved in waste collecting. We looked at governance, we identified all the actors, and we wrote an action plan to improve waste management. We implemented certain initiatives to improve water collection. Think recycling, think other kinds of projects. For example, a rainwater project. The idea is to clean all our drains, the 50 kilometers of drains that there are in the city. We took that initiative of recycling as well. You can look at it. And there are other perspectives. We want to improve awareness. We encourage businesses to integrate in their business policies better waste management practices. But please move to the next slides so that we can look at those initiatives when it comes to the source to sea program implementation. There you have it. The idea was to solve problems there in the watersheds of the Wouri. Those are the sectors that are the main sources of pollution in our watersheds. You can move to the next slide because I think I only have a few minutes left. Here, there is a study in which we identified all the stakeholders. There are three categories. The one that create pollution, then the administrations, and then the support stakeholders, the financial partners. Also, we targeted governance. Think legislation here that help us better manage waste. I said it, we implemented a global action plan. In that plan, all stakeholders have a role to play. Communities, state actors, waste producers, actors from the civil society, everybody have a role to play in that action plan. Please move to the next slide. Here are some of the initiatives. Next slide. That's been covered. Next slide. Next slide, please. That's been covered. Oh, here you have it. Here are some initiatives. We have a scheme draining project. There you go. A recycling project. There's a screen there where we actually get a screen that would collect waste before it ends up in the river and in the sea. That's a project that was put in place there. Next slide. Good. All right. Next slide. So we want to move to carry on awareness campaigns, and we want to have a legislation for packaging. Now we want to assess our action plan at this moment. I want to thank you for your time. Thanks for listening to me.
Merci beaucoup.
Thanks for your attention.
Mbocksi, for your very insightful and honestly eye-opening presentation. I've seen it in the literature, but I've never seen it firsthand. So thank you very much for sharing experience. I think this was a wonderful presentation. So with that, we're going to move to our next presenter. That is, we have Dr. Zhijie Li, who is joining us next. And Gloria works as the coordinator on plastic monitoring at a cycle program of UNiTAR. With industrial ecology background, she has been working on circular economy related topics during her academic period. Now her focus is on developing the statistical guideline for plastic flow and plastic monitoring. So with that, Dr. Li, the floor is yours. Dr. Li, you have to unmute yourself.
Yeah, sorry. Yeah, thank you. Good morning and good afternoon, everyone. I'm Zhijie Li. You can also call me Gloria. It's
Je
much
suis
easier.
Zhijie Li. Vous pouvez m'appeler Gloria, c'est plus facile. Je travaille à sur le programme S-Cycle de UNiTAR. Je veux vous présenter un aspect de notre travail afin de gérer.
So a few words about our organization. We are a sustainable cycle team. So we are hosted by United Nations Institute for Training and Research, so UNiTAR. And our team is located in Bonn office, so in Germany. And we have the foundation, the approaches towards the circular economy, towards zero waste, zero emissions, industrial ecology. And we not only conduct statistical work, we also provide support on policy, advice, capacity building and training, facilitating international dialogue, and also research. And within our team, at the moment, our main two focuses on electronic and electrical equipment and plastics. So in my presentation today, I would like to focus on our plastic work. And I would like to first introduce the statistical guideline we have been working together with the United Nations Environment Program on measuring flows of plastic along the life cycle. And then I would like to highlight the key methodologies we used in the guideline to estimate the data gaps. And at the end of my presentation, I would like to also point out some challenges we have been facing and to also introduce some our future next steps. So yeah, let's see the plastic pollution. It has been a really big topic. It's in academia, in even social media, and also policy community. It has been a big topic for years now. And since around 2 years ago, so in March 2022, a historic resolution was adopted to develop an international legally binding instrument on plastic pollution, including in the marine environment. An intergovernmental negotiating committee, so we call it INC, is convened to develop the instrument. which is to be based on a comprehensive approach that addresses the full life cycle of plastic, including the production, design, and the disposal. The INC began its work during the second half of 2022 with the ambition to complete the negotiations by the end of this year. And actually, the INC4 just concluded earlier this week, I think it's Monday, in Ottawa. And I was also there, watching closely the whole process. And over the course of the INC, delegates worked on negotiating the revised draft text. I put a screenshot here. So delegates discussed, among the other things, emissions and releases, production, product design, waste management, problematic and avoidable plastics, financing, and the just transition. And the next INC should be the last one. So it's INC 5 will be hosted November this year. And I put a screenshot here for the revised zero draft if you are interested, and you can find more information online. So with this big background, and we see more and more research about plastic pollution, we see more and more attentions about plastic pollution, but globally, there is still no agreed detailed statistical methodology to calculate the plastic flows along the life cycle at the national level. So our statistical guideline is to provide policymakers with high-quality statistics on plastic that are comparable at the national, regional, and global levels to inform policies on responsible consumption and production, the circular economy, and others. And the target users are national statistical offices and other relevant organizations who are responsible for production of statistics on plastics. And we are working closely with UNEP, so UN Environment Program, and also get support from other organizations, also with some national statistic office, for example, Statistics Norway. We also work closely with academia like University of Wollongong and many others. And in the guideline, we also include some front-runner countries example, for example, Norway, Canada, and Australia. We have finished the draft of our statistical guideline, and it has been went through several rounds of consultation. And the next round of consultation will be with the global statistical community. And we will start the pilot testing from the second half of this year. And from next year, we will do more capacity building activities. So I would like to also provide a little more details about our guideline. So we have been talking about life cycle. So what exactly are the stages of life cycle? So in the guideline, we divided the life cycle into three main phases. So supply, use, and waste. And you can see here, I listed a few key elements for each phases. And one element here, plastic waste generated, is the key element which is most related to our topic today, so microplastic pollution. Because we know that a lot of microplastic pollution comes from the mismanaged plastics. And we have statistics on plastic waste collected, but what is total amount of plastic waste generated? This information we need to model and we need to calculate them with ourselves. And in the guideline, we propose to use the methodology, product lifetime methodology. We can also call it dynamic material flow methodology. So the main idea of the methodology is that if we know how much plastic products are consumed in a particular year, and if we also know how long the products will stay in use, so we can also call it the lifetime of the products, then we'll be able to estimate when the product will become waste. So we can calculate plastic waste generated in this way. And then the question would be, the plastic products are so diverse, their lifetimes can be really different from each other. For example, the PVC floors, their lifetime can be like 10 years or 20 years. The plastic toys, their lifetime can be 2 years or 5 years. And for plastic bottle or other plastic packaging, their lifetime can be like 1 day or few days. So what shall we do? How shall we categorize the different plastic products? And within UNiTAR, we developed this a new classification system for plastic products. We call it plastic keys. So how we constructed the plastic keys? We constructed in a way that within one plastic key, the products should have similar function, they should have comparable material composition, they should also have similar end-of-life characteristics. And we can further aggregate plastic keys into 8 groups, or you can also call it 8 economic sectors, so including packaging, transport, and other sectors. So in this way, we can categorize the plastic products. And a small note here is that we only included finished products in our plastic keys. But finished products are consumed in final consumption phase, and they are not likely to be used for further manufacturing. So in this way, we only include finished products, then we can avoid double counting. And within the finished products, we still have two categories. And one is finished plastic products. And this is the products like pure plastic. They consist of plastic, like plastic bags, plastic bottle. Another category is plastic containing products, where plastic is only used as a component. So for example, electronics. They are made from plastic, glass, metal, and other materials. So in electronics, plastic is only used as a component together with other materials. And statistically, we can use plastic keys to gather information on plastic products. And as I showed earlier, they can also link to industry sectors. And also, we also provided corresponding tables between plastic keys and other statistical classification systems. So this is plastic keys in a nutshell. And we have put plastic keys into practice. We have established a toolkit. So in our toolkit, we have plastic put on market tool, we have plastic waste generated tool, and we can use them to calculate plastic consumption and plastic waste generated. And this is a diagram to show the whole structure of our toolkit. So in the toolkit, we have parameters built in, we have all the equations and all the functions already built in the toolkit. And all you need to do is just to collect the data on trade and on domestic production, and you enter data in the toolkit, then you'll be able to get the result of plastic consumption by sector, by polymer type, and plastic waste generated by polymer and by economic sector. So yeah, this is my brief introduction about our plastic work within the team. And to move forward, we would like to update the parameters in our toolkit or in our model periodically. So the parameters include plastic fraction and average weight. And we know that these parameters, they will change along the time with technology involvement, and they are also different geographically, because the countries already have their different preference on different products. So this is something we would like to get inputs from you, and we can develop them together. Another point is at the moment, polymer composition is still at sector level, and we would like to get more information about polymer composition at the plastic key level. And also, we know that all these plastic containing products, they will end up in different waste streams. And it's very difficult to trace the plastic existent in all these different waste streams. And this is also a point we would like to explore together with you. So yeah, thank you. This is my presentation today.
Thank you very much, Dr. Zhijie, Dr. Li, Zhijie, and very interesting presentation. Honestly, that simple formula that looks simple and estimates the plastic waste gives us a very simple lesson that we have to be opting for products with a larger lifespan to decrease our plastic waste. Thank you very much. We're going to come back to you with questions later on. So I am going to introduce our last but not least presenter today. Our final presenter is Professor Satinder Brar, my friend and my colleague, who is the James and Joan Love Chair in Environmental Engineering and Director of One Water Institute at York University. She's been working in 2 converging fields of value addition of waste and decontamination for the past 2 decades. For microplastics in particular, her research is around fate and transport in wastewater systems and their journey onward to surface waters. So, Professor Brar, the floor is yours.
Yes, just a moment. Is my screen visible? Yes. Okay, a warm welcome. Thank you so much, Shooka, for the wonderful introduction. So I think I can jump directly to my presentation. A warm welcome to you all. Having listened to, different aspects of microplastics, I would be delving more into the specific example of wastewater treatment plants. So as you can see, the title of the topic is Missed or Slipped. Missed is derived from our research program, which is on microplastics in sewage sludge exploration and detection. And why do we call it slipped? Because you will understand as we move through the chain in the wastewater treatment plant, then, are we missing them or do they slip through it? Let's find out. So here in this slide, you can see a typical wastewater treatment plant. I would say microplastics and wastewater treatment plants, there is a nexus. And, Denise had already explained how these plastics break down into microplastics. So I don't need to get into those details, but just to let you know what actually enters as wastewater into our typical municipal wastewater treatment plants is the industrial water, wastewater, hospital wastewaters, domestic wastewaters, and even stormwaters in some cases. And this is what ends up in these wastewater treatment plants. And these percentages that you see here, they are actually, starting from 100% of microplastics, ending up to 1% microplastics, which reach the final surface water stream. And likewise, 90% of the microplastics, which are hidden in these wastewaters, are actually finally ending up in the wastewater sludges, which is the solid part of the wastewater treatment plant. So let's deeply understand each of these treatment steps. You can see here primary treatment. This is the first step in a wastewater treatment plant. And the typical objective of this process is to remove large solids and inorganic matter. So some amount of microplastics does get removed, especially the larger particles, during the screening, grit removal, and sedimentation. But afterwards, this effluent is now entering into the next step, which is the secondary treatment. So here you can see one of the students, Gaurav, he's gone to collect the secondary wastewater from the wastewater treatment plant. And here what happens is we have the biological degradation happening because we have microorganisms sitting there. They are, eating up the organic matter and clarifying the water, which finally turns out to be a secondary effluent. And now this secondary effluent then finally goes to the tertiary treatment, which is the last step in the wastewater treatment plant chain. And this secondary effluent in some of the plants can go through filtration, or it can even directly go to the disinfection step. And that's how we get the final effluent. And in some other wastewater treatment plants, like here in Montreal, in Canada, we have the advanced oxidation ozonation process in Montreal, which is, I would say, really a state-of-the-art wastewater treatment plant, getting up to a final clear effluent, and this is what ends up in surface water. And we'll find out later, how and what happens to these microplastics. Of course, Denise has already touched base on their fate in the surface water. And typically, tertiary treatment means we are doing the disinfection so that we don't have those pathogens ending up in the treated wastewater when they land up in the surface water. But last but not the least is the sludge management part of the wastewater treatment plant as well. So this is the, I could call it the compartment of the wastewater treatment plant where actually the sludge is thickened and it needs to be stabilized because there are so much organic matter there. And then we remove the water so that it becomes, more concentrated. And finally, it could be ending up either in landfills or land applications for farming, or even incinerated in some cases. So the key function here is just to reduce the volume of sludge, because we would have large volume of solids. Remember, there's a lot of water in these solids as well. Now let's understand why we need to understand this entire wastewater treatment plant chain, because we have the detection paradigm here as well. So a wastewater is like I would say like a soup which contains organic and inorganic matter. And now our microplastics, they could be embedded, they could be encapsulated, they could be hidden, they could be missed within this organic and inorganic matter. So in order to, swim through this wastewater and actually capture those microplastics, we need to do some kind of treatment for the sample. And this is what we call as pre-treatment. And when we do this pre-treatment, this also helps us to eliminate if there are any false interpretations, while we are doing this pre-treatment. And what do we do here in our lab is, so here you can see Juvia. So Juvia goes to the wastewater treatment plant, collects the sample, and brings the wastewater sample. Since we don't know what we are looking at, it's a soup. So to start with, we naturally have to spike it or fortify it with the known microplastics, and then we do some kind of pre-treatment, which would, sort of eliminate a larger chunk of the organic matter. Finally, we do the filtration and we do qualitative and quantitative analysis. For simplification, I'm just putting in some pictures here to understand did our pre-treatment work. So here you can see in the top row is the virgin microplastics, and in the lower row are the microplastics post pre-treatment. So basically, visually, they look similar, and this is what we want, because we don't want the pre-treatment to affect the microplastics per se. We just want the organic matter to be eliminated during the course of pre-treatment. So here we are still continuing our work and trying to devise different methods. As you have commonly heard, there is no standard method. So we are also at a crux when we are trying to see, how we can optimize different methods for analysis. Now, moving on from the detection paradigm on to next part of the wastewater treatment plant chain, which was the secondary treatment, where we had the microbial systems. So here, typically in a wastewater treatment plant, we have the suspended growth system and attached growth system, or the microorganisms could be suspended or they may be attached on a surface. Now you can understand that microplastic in itself is a surface. So it is a very good surface which would allow these microorganisms to stick to them and start forming colonies, aggregate. And this is, in future, a potential source of other pollutants being sort of, also accumulated on the same surface, or pathogens, or even the antibiotic resistance bacteria. So here in our laboratory, Gaurav, what he does is he simulates the wastewater treatment plant, typically these two processes you can see here, to understand the transport and fate of biofilm-associated microplastics. And in our initial studies, we have seen that biofilm formation varies with the microplastic type. So, as you vary the microplastics, the sticking of the microorganisms to these microplastics, it varies as well, because each microplastic is different, chemically speaking. So the bonding of the microorganism to these microplastics also naturally varies. Now, with respect to this, we are also trying to understand that when these biofilms are formed on the microplastics within the wastewater treatment plant. So here, Mariam, what she does is she goes to these wastewater treatment plants and she's putting these tiny tea filters within the wastewater treatment plants, letting the microorganisms stick onto the microplastics and understand if, this would eventually, this biofilm would be a carrier or vector for pathogens. As you can see here, it is naturally possible because of their surface that these microplastics can actually provide the surface for sticking of these microorganisms there. So here on the left-hand side, you can see this is a natural particle, typically after 2 months of incubation in a secondary effluent in the wastewater treatment plant. But when Mariam actually left her high density polyethylene microplastics, after 2 months of incubation, you can see there was a change on the surface here, and this is what she's trying to understand, whether there was some sort of weathering that occurred, as well as whether there was sticking of any microorganisms. And finally, the last, after the last compartment of tertiary treatment, all this ends up in the surface water. And we have heard a lot about, from Denise, how they are analyzing these microplastics in surface water. Likewise, we are trying to understand here in Canada, in the surface waters, how these microplastics actually manifest. And here, Behnam, what he does is, he's collecting samples, for example, from this Hamilton Harbor. Likewise, we are doing some studies with Lake Ontario to find out how the layers of lakes, where the temperature changes can be different, sort of changes the presence of these microplastics in terms of their size fractionation. And this is very interesting for us to see as we are moving forward in this as well, because after all, this is the last leg after the wastewater treatment plants. So I would say the lessons that we have learned so far, we are still far away from reaching the final conclusions. It is very interesting and important for us to understand that wastewater treatment plants are the source and sink of these microplastics. So we naturally need to develop standard, there's no possibility of standard detection method, but some kind of detection within that complex cocktail. Likewise, if we want to understand how these microplastics manifest, we need to simulate the reality in the lab. We need to understand if they can really act as vectors as we move forward, and could be, carrying other kind of pathogens across waters. And of course, once it gets into those surface waters, beneath the surface, what actually happens to these microplastics once they have slipped in to the surface layers. Now, last but not least, again, after having understood that microplastics, have been causing all these adverse impacts, and that we need to study their fate and transport, are there any alternatives? We need to understand, of course, there are. But these alternatives are also not magical. After all, if there is no control at source for the typical plastics, so this is, just a drop in the ocean, I would say, as an alternative to the regularly used plastics. Here in our laboratory, we typically work with biocomposites and cellulose-based plastics and PHAs. I couldn't speak much about it because of the proprietary information related to these research projects. And I think that brings me to the end of this presentation. I would like to thank the wastewater treatment plants who have been actively participating with us on this project, and other research partners. And thank you so much for the panel here, and I look forward to the questions. Thank you.
Thank you very much, Professor Brar. I would now like to invite all the panelists, Professor Mitrano, Dr. Zhijie, and Madame Mbocksi, to turn on your cameras and your audios, please. Madame Mbocksi, I don't see you. Please turn on your videos. So we're going to have a quick round of questionings, and I would appreciate if you try to limit your answers to 1 minute, because we're simply running out of time. I'm going to go to Professor Brar, because you mentioned about alternatives in your last presentation. So can you explain a little bit more, probably in that 1 minute, what are your views on conventional plastic alternatives and, for example, the biodegradable plastics that you just mentioned?
Thank you so much, Shooka. Yes, biodegradable plastics could be an alternative to the synthetic plastics, but we should not forget the whole plastic in itself may not be biodegradable, because it's very difficult. You have to blend it with other components, and some of those other components then are still chemicals, even if some portion of it is biodegradable. So it's a very complex equation, you know, when we call them bioplastics in itself is a nuance, because some of them can be bio-based yet not completely biodegradable, and they can be biodegradable and not bio-based and could be partially biodegradable, and so on. So I would say that it's a good you know, good way to do it in complementarity, but definitely it's not the solution as well.
All right, thank you very much, Professor Brar. Denise, if you don't mind, I know there is, including this webinar that we're having wonderfully hosted by UNiTAR and York, there are a lot of educational initiatives around raising awareness for the public on plastic pollution. What are your views on these educational tools?
Oh, well, I mean, I think that it's great that people are very engaged. Of course, it brings a real call to action and at least more information for a lot of people to get in touch with. Although the question that I'm always asked is, then what can I do as an individual person to be able to reduce plastics pollution? And besides, you know, having an own personal waste management strategy, I think that it's really trying to vote and have these bigger initiatives that can tackle some of the systemic problems of plastics pollution. So that's not to say that individual choices don't matter, but I think that by having larger systemic solutions is really how we will make more sustainable plastics and a better plastics life cycle and circular economy in the end.
All right, very good. Absolutely. Thank you very much, Denise. Anybody would like to add to Denise's answer? We probably have a minute. Zhijie.
Yeah, of course. Yeah, I was maybe at my personal experience when I was following the INC 4 in Ottawa. I was like, I'm not a policy person. I'm more like a data person. But according to my personal experience, it's amazing to see like 170 member states are there. Like there's hundreds of observers there. They like everyone have this willingness to deal with this plastic pollution altogether. And I think that is really, really amazing. And yeah, all this INC process or all this our work together can also serve as a platform for everyone to just learn from each other. So we can share the technology, we can share the knowledge with each other. So I think everyone's engaged in this process, and then we can help each other all together. Yeah.
Absolutely. Thank you very much. I actually answered my question about INC. INC is a platform bringing everybody together, sharing solutions, and possibly coming up with a global solution, because even though it is domestically sourced, we have a global problem. Thank you very much, Madam Mbocksi. My last question is for you. And you have wonderfully shared some of the tools that your community uses to tackle locally with plastic pollution. What are some other innovative ways that you think your community and other local communities can actually use to tackle plastic pollution locally?
qui concerne ma localité en matière de... J'espère avoir bien compris la question. Hein. Je crois que la question concerne le recyclage des ordures. Je crois que c'est ça, la question que vous avez posée.
Oui, yeah, oui.
Voilà. Donc, ma communauté, en ce qui concerne le recyclage des ordures plastiques, a pris certaines initiatives. Nous sommes en train de faire... nous avons eu un projet nous récoltons, c'est un projet de fabrication des pavés pour les routes, pour avoir une solution alternative des routes. Et nous avons aussi mis en place, on a construit dans les drains, on a construit des ouvrages pour collecter, pour empêcher que les ordures ménagères les plastiques n'aillent dans l'océan. On a construit des ouvrages. On a construit des ouvrages pour capter tout ça. Et puis, avec Et ça fait aussi l'objet d'une sensibilisation autour des déchets plastiques. Nous avons aussi un projet de construire une usine de transformation et de recyclage de ces objets. Et on a pris la réglementation aussi est en train d'obliger les entreprises productrices de déchets d'intégrer leur recyclage dans leur politique. Voilà, résumé, ce que je peux vous dire.
Thank you very much, Madam Mbocksi, and thanks. Thank you very much, everyone, for your wonderful presentation. We have run out of time. I have a series of questions for everybody, which unfortunately we didn't get to go to them. And we have a lot of questions in the audience in the Q&A that we didn't get to go to as well. We're going to reach out to you and get to your questions, so please stay tuned. And thanks again to our wonderful host, UNiTAR and York University for organizing this panel, and to our wonderful panelists who has joined us join us and shared their expertise and their time. Thank you very much, and have a wonderful day.